Hello, I'm Amy and this is Lab 3, Black Hole and Orbits. This lab has two main parts. In part 1, we determine the mass of a black hole by analyzing the motion of a star orbiting it. In part 2, we simulate a spaceship traveling through a system containing a planet and a moon and find a velocity that allows the ship to move through the system without crashing. The purpose of this lab is to analyze orbital motion using position data and use that motion to calculate velocity, momentum, and net force. Using the rate of change of momentum, we can determine the gravitational force acting on the star and estimate the mass of the black hole. In part 2, we use a computational simulation to study how gravitational forces affect the motion of a spaceship moving through a planet-moon system. This lab is based on several important physics principles: Newton's second law, F equals dp over dt, momentum is P equals mv, gravitational force, and these equations allow us to determine the gravitational force acting on the star and estimate the mass of the black hole. In part 1, the system is the star and the surroundings is the black hole. In part 2, the system can be the spaceship or the moon, while the surroundings include the planet and other bodies applying gravitational forces. This model uses several known constants. The gravitational constant, the star mass is 2 times 10 to the 30 kilograms, and then the time step between position measurements is 1 day. The orbit of the star is generated as an ellipse using a computational model. The program calculates many position points along the orbit and stores them as x and y coordinates. These points represent the motion of the star around the black hole and are used to determine velocity and force. Here is the velocity calculation. It is calculated from changes in position. Net force is calculated using rate of change of momentum, and here is the code for that. And for parallel and perpendicular forces, the net force can be separated into parallel and perpendicular components, where the parallel component changes the magnitude of momentum, and the perpendicular component changes the direction of motion. For my black hole mass result, using the gravitational force equation, we can solve for the mass of the black hole, and then I got around 1.62 times 10 to the 34 kilograms, and this is calculated from averaging different values. In part 2, the simulation models a spaceship moving through a system containing a planet and a moon. The spaceship experiences gravitational forces from both bodies, and using Newton's second law, the simulation updates the velocity and position of the spaceship over time to produce its trajectory. This model prediction matches the expected physical behavior. Objects accelerate toward massive bodies due to the gravitational attraction, and orbits occur because of the centripetal force. Small differences appear because numerical approximations and time steps in the simulation cause minor errors. Possible sources of errors include numerical approximations in velocity calculations, the use of discrete time steps, and rounding. In part 2, the spaceship velocity was also determined using trial and error, which may not produce the best trajectory. The rate of change of momentum describes how quickly an object's motion changes. According to Newton's second law, this rate of change of momentum is equal to the net force acting on the object. This means we can determine the force on the star simply by measuring how its momentum changes during its orbit. If we wanted to model the system more realistically, we would include gravitational interactions between all the objects, including the black hole, star, planet, moon, and spaceship. Some forces dominate, such as the black hole's effect on the star, but smaller interactions would still influence the motion of the system. So in conclusion, we used Newton's second law and gravitational physics to determine the mass of a black hole from orbital motion. We also used a computational simulation to model how gravitational forces affect the motion of a spaceship in a multi-body system. And these results demonstrate how physics principles can be applied to analyze orbital systems. Thank you.